Alright, well hello again. I'm back to give you kind of a part two on that little video that I did previously about the kernel of a linear transformation. There's one other subspace that I want to talk about as well. The kernel, just to remind you, it's those vectors that get killed by t. In other words, they get transformed to the zero vector of w. And the kernel of t forms a subspace of v. Alright? Turns out there's also an important subspace that we can associate with this transformation that is actually a subspace of w. And even though v and w could be very different as vector spaces, it turns out, and I'm going to talk about this later, not in this little video right now, but it turns out that there is a connection between the kernel of a transformation, which is this subspace of v, and the subspace I'm about to talk about, which is a subspace of w. Okay? What the subspace is that I want to talk about inside of w is called the range of the transformation. So we abbreviate that RNG. So the range of the transformation. What that is, as I was showing you on this picture before, you have sort of vectors being transformed from the left side to the right side. A lot of them might be going to the zero vector, but you also have other vectors here, and the range of t is that part of w. It's that part of w that actually consists of vectors that arise as outputs of the transformation. So you see, my point is, you could have some vectors in w. W could be really, really big. And there could be some vectors in w that just don't get hit by an arrow coming across from v. In other words, there could be no vector from v that maps onto one of these dots up here. Okay? So the range of t is the set of, I'll write it this way, the w's in capital W, such that w is equal to t of, and I need arrows on my vectors, w is equal to t of some vector v, so this is for some v in capital V. So it's those vectors that actually show up as outputs of the transformation. Okay, another way to write this is it's literally just the set of all possible transformed vectors. So if you take every single vector, little v, from the vector space capital V, and you transform every single vector, then you get the set which consists of the range of t. Okay? Now, that sounds like a lot of work to find the range of t because there's a lot of vectors here to transform. So this is potentially a very big job to calculate this range of t. So that's what we need to do next, is address how do you calculate the range of t, and then we're going to look at it again in the context of a couple of examples. So here's the thing, and this is where some of the chapter 4 stuff really starts to pay off for us. If we imagine that v1, v2, up to vk is a basis for v, right? Then, of course, I could transform each of those basis vectors, and that would be part of what I need to compute to find t of every vector. But what turns out to be true, this is really quite remarkable, is that you can express the range of t as the following span. All you have to do, my friends, is just literally transform the basis vectors only. Just the basis vectors. That's all you have to transform. That's not very many vectors. That's just a small little handful of vectors. You just have to transform those ones And then the point is, if you take all possible linear combinations of those, which is what the span is doing, you're going to get all of these. You're going to get every transformed vector. It kind of makes sense because, after all, every vector, little v, is expressible using just these guys. So if I know how these guys, these basis vectors from v, are transformed, then any other vector can be transformed by just expressing that vector in terms of this basis. You just need to find these guys right here. Okay? So this is really the best formula for actually calculating the range of T. And again, what is this set? It's a subspace of W. Oh, by the way, it's kind of obvious that it's a subspace, because anytime that you take the span of something, you get a subspace. So we don't even have to justify that part. That's just a freebie. It's the span of something, so it's got to be a subspace. Now, the vectors that are in this list, they certainly span it. They span the range of T because they, I've said this before, these vectors span whatever they span. Okay? So they are a spanning set. These k vectors, T of v1, T of v2, and so on, those are a spanning set for the range of T. Be careful, however, because there could be linear dependencies in here. So you guys have seen problems in the previous chapter where we had to sort of throw some vectors away that were linearly dependent in our set. The same thing can happen here as well. Okay? So I think that will become clear as we do a few examples. Okay? So this is the range of T. It's just all possible outputs of the transformation, which might or might not, usually won't be, all of W. Okay? But it's all possible outputs, and the best way to get that set is to literally just transform a basis for V. You can choose the basis for V to be whatever basis you want. Usually you're just going to use an easy one that you automatically know. But any basis will work. You just transform each of the vectors from that basis and take the span. Okay? Let's do an example. Actually, let's go back to the one that I did in the other video clip about the kernel. We were doing T from R3 to M2 of R. And I think we did it via, it was T of ABC equals 0, and then A minus B plus C, and minus A plus B minus C, and 0. Okay? And I asked you to take my word that it's linear, and also that, we calculated the kernel by setting this matrix equal to 0 and solving for A, B, and C. Okay? Let's find the range of T. So if we're going to use this boxed formula to do that, we need a basis for R3. So I am going to suggest we use the standard one because that's the easiest one that we all know. Okay? So according to this formula, if we want to find the range of T, all we have to do to find the range of T is we just simply have to take the span of T of 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1. These are my basis vectors. Okay? So let's just calculate these things. T of 1, 0, 0. How do we calculate that? Well, we're putting in 1 for A, 0 for B, and 0 for C. What you'll notice if you put in 1 for A, 0 for B, and 0 for C is that you get this matrix right here. So that's the first vector in this set. Then we have to do the same thing for T of 0, 1, 0. So that means I'm putting in a Z. If I want to evaluate that, I have to put in 0 for A, 1 for B, and 0 for C. Right? So if I put in 0 for A, 1 for B, and 0 for C, I just get this matrix. Like that. Okay? And then I have to do 0, 0, 1. For that one, I'm going to put in 1 for C and 0 for A and B. So I'll get 0, 1, negative 1, and 0. And you kind of already see the point that I was making before about the fact that although I have 3 vectors here, you notice that they are definitely not Li. In fact, the first one and the third one are the same, and the second one is just the negative of the first one. So actually, this thing is literally just the span of the very first matrix that you have in that list. That's the only one you have. So it's only, this is a basis, it's just this one 2x2 matrix. That's a basis, it's one-dimensional. Okay? So even though you've got a long list of transformed vectors that you're putting into this span, that doesn't mean you have a big space, right? If these vectors are LD, right, well then the dimension isn't that big, right? You can throw some of them away. And of course, to know which ones to throw away, remember we have a process for throwing things away. You put each one of these matrices in the columns of another matrix, right? And you do your EROs and you look for linear dependencies. In this case, the second and third columns would have no pivots, which would mean that they were corresponding to linearly dependent vectors from the set. Okay? Let's try another example. Let's see if I can remember. I think we did one t from p, what was it, p3 of r to p2 of r via, oh, you know what, before I go on to that, one last thought over here about this example. Notice that the space W was all 2x2 matrices, which is a four-dimensional space. It turns out that this transformation does not hit very much of that four-dimensional space because we only got a one-dimensional range. So again, although W, which is the receiving space for this transformation, is quite large, the actual elements that come out of this transformation comprise a very small part of that space W. You can kind of see it just from the form of the matrix, right? This is a very restrictive form. You have to have a 0 here, you have to have a 0 here. These two entries are negatives of each other. By the time you impose all of those constraints, you only get the matrices that are multiples of this one. That's all you have in this range of T. Okay, so I just wanted to make that clear. The space W can be huge, even though the space of the range of T could be much smaller. Okay. Okay, so I had this example earlier. It was basically T of P of X equals P double prime of X minus 3 times P prime of X. I hope that's what I had. So I'm going to use P3 of R and P2 of R. Okay? And let's try and find the range of T. Now the idea is that we can use this boxed formula. And in order to do that, I have to have a basis for V to start with. And I can choose any basis that I want. So for a basis to work with, P3 of R, the nicest basis that I think most of us would agree that we could work with, would be this one here. Okay, just the powers of X. Okay, so the range of T is just the span of, give myself a little bit more room here now. You can always rewind the video if you need to see this again. No need for me to worry about it. Okay, so it's just the span of T of 1, T of X squared, and T of X cubed, right? That's what this says. Take the span of the transformation of the basis. Okay? So all we have to do is transform, using this formula in the box here, transform each of these four things. If I plug in 1, then I got to take 2 derivatives of it and subtract 3 times 1 derivative of it. That gives me 0. So far I haven't spanned anything. Okay, so we're not getting much so far. By the way, notice I'm just leaving my polynomial abstract here. I'm not writing it. I think when I did the kernel, I rewrote it as ax cubed plus bx squared plus cx plus d. I don't have to do that here because I'm just plugging these vectors into this formula, which I can do even if it's written abstractly. Right, so that's kind of nice. All right, what is T of X? Well, if I put in an X for my polynomial, This says you have to take two derivatives of it. That gives you 0. Minus 3 times one derivative of it. Well, one derivative of x is 1, so we're just going to get minus 3. Okay? X squared. If I transform x squared, I've got to take two derivatives of it. Two derivatives of x squared is actually 2. Minus 3 times one derivative of x squared. One derivative of x squared is 2x, and we're multiplying that by 3, so 6x, which we have to subtract. Okay? And then the last one, t of x cubed, I have to take two derivatives of x cubed. That's going to be 6x, and then minus 3 times one derivative of x cubed, and that's going to be minus 9x squared. I think everybody can probably handle that. Okay? So if I ask you what's the range of t, you could literally just say, there it is. It's the span of these four things. Of course, we know that this one doesn't need to be in there. It doesn't really matter that we put 0 in there or not, because we're talking about all linear combinations of these polynomials, and 0 can always be achieved by just choosing the coefficients of these vectors to be 0. So, as far as the remaining three polynomials go, do you believe that they are linearly independent? You see, these first two are not multiples of each other. When you only have two, when you're only looking at two vectors, you just have to ask, are they multiples of each other? So these two guys are Li. But if you form all possible linear combinations of them, you're not going to get this entire set because there's no x squared term. So this guy over here is not going to be expressible in terms of these two because he's got an x squared on it, right? So these two do not depend on, or this one does not depend on these two. So these are Li. So these three polynomials right here would be a basis for the range of t. Actually, that brings up something kind of interesting, because you'll notice this is three-dimensional. 1, 2, 3. And my whole space W that we started with, which is P2 of R, was three-dimensional. So I have a three-dimensional subspace of a three-dimensional universe W. And that actually means if it's a three-dimensional subspace of something that's three-dimensional, it has to equal the whole thing. So actually, the range of t is actually, so now we know that the range of t, we may not have realized it originally, but the range of t is all of W. It's all of P2 of R in this case. There's a word for that. We say that the transformation is onto if the range is all of W. But don't worry about that too much. That's kind of getting ahead of where we are. But the range in this case is all of W. A lot of the stuff we're doing here, guys, is just building off of Chapter 4, right? We're making a few new definitions here, calculating a few new things, but the kinds of ideas that are involved in thinking about what's going on is just more of the Chapter 4 material. So hopefully this is helping to reinforce that a little bit. Okay, let's see. Let me just make one more comment here. I had mentioned, so maybe for a third example, I had mentioned that if you have an M by N matrix, right, and you take T to go from Rn to Rm via T of x equals Ax, right? I've mentioned if you consider this transformation, just recall that the kernel of T was just literally the null space of capital A, right? It's because you're just setting this output equal to 0 and solving for x. Well, that's exactly what the null space is. Okay. You might wonder what the range of T is. For this kind of transformation, you might ask, what is the range of T? Well, you could use this formula. You need to have a basis for Rn. I would suggest just the standard basis. And for example, what you'll notice is that if you take A and you multiply it, so if you apply the transformation to the standard basis, so you calculate that, so basically this is equal to the span of what I'm calculating here, right? So I'm literally just taking A and I'm multiplying it on the right by one of my standard basis vectors, right? If you think about what this gives you when you multiply capital A by this column, you actually just get the first column of capital A. Because this 1 grabs the first, whatever's in the first entries of, as you go down each row, you just get the first entry being multiplied by 1, everything else is 0. This one, just the second entry in each row gets multiplied by 1 and everything else is 0, so you're going to pick off the second column of A. This one's going to give you the third column of A. So just for your info, the range of t, in this case, I know I'm doing it a little bit quickly, but it is literally just the span, remember it's the span of all of these things. It's the column space of the matrix. Okay. The subspace of Rm, just as the null space is a subspace of Rn. Yeah, so this is a familiar example that does relate back to some things we've talked about before as well. Okay? Computationally, the range of t in some ways is easier than the kernel because you have a formula for it. You just have to choose a basis for v, transform all those guys, and throw the word span in front of it. If I ask you for a basis for the range of t, then you have to be careful. These vectors in this set, they will span it. They will span the range of t, but they might be LD. So you have to make sure that you throw away any vectors that might be linearly dependent. Okay? All right. Well, that's at least a little start on this. I'm going to do some more examples of it in class. I'm going to review some problems on it in the review session. But it's great if you've had a chance to watch this video because that way when you see it coming around a second time, I'll use different examples as I do it in class and in the review. You'll already have had some exposure to a few examples here, and I think that'll be good. So thanks for watching, appreciate it, and thanks for your hard work and studying. I hope things are going well, and if you need to talk to me or if I can give you any help at all that might sort of piece this stuff together for you, I really do hope that you'll come in, and I'm definitely anxious and ready to help you if I can. Okay? Thanks. Have a good weekend, and I'll see you soon. Bye.